Welcome to Doing Better Than Expected, adjusting a country's Olympic Games ranking by including its population. Here are the top 4 of the 2024 Paris Summer Olympics, ranked by 2 different measures. On the left, ranked by gold and total medal counts. On the right, by medals per capita. So let's look at more detail. The 2 top charts show competing countries ranked either by gold or total medal counts. They look similar. In each case, 2 of the most populated countries, USA and China, dominate the ranking, followed by an almost identical group of countries with much smaller populations. In contrast, ranking by medals per capita is dominated by countries with small populations and low gold or medal counts. Shortly before the 2024 Paris Games commenced, a peer-reviewed paper was published in a learned journal proposing a different ranking scheme. It's based on a country's total medal tally and its population, with its actual score compared to an idealised probability model. It received global media attention. In a very thorough analysis, the paper also detailed the problems associated with those previously illustrated and other ranking approaches. And this is the outcome of their probability ranking model. Notice the fanning out of the slices to a more equitable arrangement, and the lowering or absence of countries having the largest populations. So what follows is a condensed guide to the author's ranking scheme, descriptive of the ideas behind the model, rather than the mathematics involved. But first, we need to discuss entry quotas. The International Olympic Committee sets entry quotas for the Olympic Games based on several factors, including popularity of the sport, geographical distribution, performance level, development of the sport, and fairness and equity. Entry quotas affect the maximum number of medals a country can win. For the 2024 Games, the total number of medals awarded was 1,045, and the theoretical maximum number of medals an individual country could win was 560. Team sports also affect this theoretical medal tally, as only one team can participate from any one country. There were 12 team sports in the 2024 Games. So here's an overview of the probability ranking model. Create an idealised reference model based on chance, total medal count and country populations for predicting medal tallies. Secondly, calculate actual Games results with this reference model. Next, compare the two by measuring the improbability, that is the unlikelihood, of the actual medal tallies being attributable to chance alone, and then apply this measure as a ranking criterion to each competing country's performance. In the creation of an idealised reference model, there are some basic assumptions. The first is, given entry quotas and other qualifications, the authors propose that the populations of all competing nations have equal capacity and motivation per person for winning medals, and this implies that all competitors have an equal chance of winning a medal, and that medal-winning achievement scales in proportion to national population. This allows medal success to be treated as if it were a random event, and permits a country's population, relative to others, to be included in estimating such statistical measures as expected medal wins. It also assumes that medal successes are independent. The chance of winning one does not influence the chances of winning others. This is the definition of an expected medal count. It's the fraction formed by dividing the population of a specific country with the sum of the populations of all medal-winning countries at any Games and multiplying it by the total medals on offer for a particular summer Games. For example, for the 2024 Paris Games, the host nation, France, with a population of approximately 66.5 million, had an expected medal count of approximately 9. As you can see, based on population alone, it would result in very inequitable expected medal tallies, as only 3 countries, India, China and the USA, would have swept up just over 50% of the medals. So to temper this domination of countries with large populations in a ranking model, the notion of the chances of winning a medal is introduced. Suppose for each country SI, the chance of winning a medal has a probability of PI. Then the authors show, using a standard statistical relation, this expression. In other words, The probability of winning a medal is equal to a medal factor multiplied by a population factor. Best illustrated with an example. For France, the probability of winning a medal was about 1 chance in 61. For the USA, with a much larger population, it was 1 chance in 12. These numbers are only approximate. They depend on the sources of data for a country's population and even the time of year when they were counted. But what is the probability of winning more than one medal? With the theoretical maximum of 560 medals that can be won by an individual country, there are many ways for achieving medal successes, different combinations of athletics events, for example. As a consequence, we have to calculate a second probability, one that combines the chances of winning one medal with the many ways of winning multiple medals. In general, such probabilities are based on two options: winning or losing, success or failure, flipping a coin. All follow the same mathematics of binary chances. So, skipping over the sordid mathematical details, the probability of winning n medals out of a maximum of m medals is equal to the number of ways of winning n medals out of m medals multiplied by the probability of winning a medal n times multiplied by the probability of not winning a medal m minus n times. So if we apply that prescription to actual games results, we find that the probability of multiple successes is extremely low if medal wins are regarded as random events. For example, France won 64 medals, so the probability of these successes, according to the idealised model, is 1.564 times 10 to the power minus 33. And for the USA, with a medal count of 126, their probability is 4.07 times 10 to the power minus 25. Now these are minuscule numbers. As a reminder of negative powers of 10, consider 3.3 times 10 to the power minus 9. It can also be expressed as 0 point with 8 zeros following the decimal point 33, and it's a much larger number than those country probabilities. Incidentally, for the record, these are the calculations for France and the USA. The minuscule values of the actual probabilities, as measured by the idealised model, indicate that they are not the result of random chance. Moreover, since these improbabilities are quantifiable, they can serve as a useful measure for comparing medal tallies between countries. The authors symbolise this measure as a probability ranking index, U, and they define it as the negative logarithm to the base 10 of the improbability value. The what? Similar definitions are common in science for transforming large or small powers of 10 to people-friendly numbers. For example, the Richter scale for earthquakes, pH for acidity and alkalinity, radioactive decay, and so on. Earlier, it was calculated that the probability of France winning 64 medals by chance was 1.564 times 10 to the power minus 33. By taking the negative logarithm of this value, we get the ranking index for France, U, is equal to 32.81, a more practical format for comparing medal counts. The authors modified this definition with a preferred cumulative probability ranking, which is the probability for a country to win as many medals as it actually did, or more medals, up to the maximum achievable. For France, its 2024 cumulative probability rank is 32.75. For the USA, U equals 24.23. In practice, there's very little difference between the ranking based on the actual medal tally and the cumulative value. Again, just for the record, the equation for the cumulative probability ranking index UC is this. And that's the equation by which the authors constructed their probability ranking scheme for the 2024 Summer Olympic Games. Concluding with some comments, the idealised probability model is founded on the premise that the populations of all competing countries, including the very small fraction of their eligible and qualified competitors, quote, have equal capacity and motivation per person for winning medals. Of course, this is contestable, but as the authors state, it's a theoretical tool for ranking only. We never use it to predict medal-winning results. Although the model's mathematics, probability and binomial distributions, are based on topics taught in senior high school classes, Their application is more nuanced than simple medal count comparisons which ignore populations as a consideration. As with the Duncan Parece model, it's common for complex ranking systems based on multiple factors to have simple outcomes. One that we may be familiar with is a probability-based method called Bayesian statistics, instrumental in predicting the next word during text input by suggesting the appropriate one ranked first in a list. A nation's preference for a ranking system. The reality is a nation's citizens and its fourth estate will prefer a ranking system that favours their own. Nevertheless, given the global addiction to gambling, a ranking system based on chance might just prove to be a winner. It's to the authors great credit that they developed and published a scientifically based probability model which ironically led to their own country's rank being reduced. Thank you for viewing this video.